Okay,
How
see,
about try 200 before 255?
you want to try 200 instead of 255? All right, so I'm now recording. It's day 2 of week 5. Yesterday I was running on no sleep. I had pretty bad insomnia the night before, and so I was sort of coding without really having a brain that worked too well. So, okay, so yeah, it's the barycentric coordinates are actually not correct on this. So let's see if we can explore what is going on here. Okay, so so we're creating a vertex buffer. Similarly, you've seen this before, right? The vertex buffer.
Yeah, so I'm assuming the first 3 are coordinates and then the second 3 are color.
That's correct. Yeah. Let me just make sure that the coordinates aren't doing anything weird. Okay, good. All right. So yeah, row, column, depth, R, G, B. Row, col, depth, R, G, B. So we're using a coordinate system that is an orthographic projection, which means instead a normal camera kind of goes out like this. You have like a field of view, and an orthographic projection is sort of like what's used in a lot of action RPGs. So there's not like a perspective. Instead, what happens is like if you had a quarter like this, normally in a quarter, the points are going to come down towards a vanishing point because you have perspective. But an orthographic projection, you're looking down from every pixel equally, and that's very common in like action RPGs because it would be weird for like things over there to be like occluded by a wall, and then as you get closer, you can see it. Instead, you can kind of look down equally from every point on the screen, which isn't necessarily like a physical thing, but it does simplify. Like StarCraft and games like that would be an orthographic projection because you're not like seeing the side of, like if there's a cliff, you don't see the side of it and the side of it. You look down at both from above, and as you scroll around, you don't see like the pillars, like you see one side and the other side. Some games probably do use perspective projection matrices, but for us, we're using orthographic because it's easier, and we can do projection next if you want. So, all right. So let's debug our barycentric coordinates because, like I said, I wrote this with like almost no sleep last night. So let's figure out the math first because it's better to understand theory than it is to just guess blindly like I did yesterday. So let's talk about barycentric coordinates. And so for barycentric coordinate, pen, there we go. All right. No, let's not use the rainbow one. Let's do blue. So we're gonna have a blue pixel or blue vertex. We'll say this one's red, whatever. And you can be green. Actually, we'll just make you red. Okay, so if we have, then I'll use what color line? White, just so we don't think. So currently the thing is lerping correctly. So for our linear rasterization, it works correctly. If we look over here, look over here, and you can see we've got a purple vertex, a blue vertex, and a green vertex. As we travel along the line, it is successfully lerping along the way. Our line rasterization looks quite fine. We have a precondition that the points are all in clockwise order, and if we were smarter, we would add in a check for that. So when we construct the triangle, we probably shouldn't be doing it all pods style like this. We should have a constructor, and the constructor should actually verify the points are, in fact, clockwise. But they are, and so that's not the source of our bug right now. Possibly yesterday, they might not have been. Who knows? But okay, so I guess the first thing we need to figure out is if our cross product is actually correct. But let's go through the theory first. Okay, so if we have a point here, if we have a point right here, then the barycentric coordinates is the relative ratio of this. So this, the size of this triangle, and it's really going to be, it's actually going to be a quadrilateral because we don't need to divide by 2. This is created, this is a dot product. All right, I keep saying dot product, cross product. So this is the cross product of this vector here and this vector here. That's the cross product. And so the vector from blue to green is cross producted with the either of these. You can either use this one or this one, it doesn't matter. With the vector from, we'll call this point P, the cross, I'm just going to use one letter instead, forgive me, red, blue, green, and P. These are our 4 points, okay? So the cross product of vector of blue to green crossed with the vector from blue to P is the size of R, capital R. Capital R is this area here, okay? And this is going to be a big number because we're close to R, lowercase r. Do you guys see that? So like, let's say the area of this is 100, and the area of this is 10, and the area of this is 10. Then the total area is 120, and so this R, capital R, divided by 120 is 10/12, which is 5/6. So R is 5/6, and then G, which is formed by the cross product of this vector and this vector. So G is the cross product from red to blue crossed with the vector of red to P. And blue is formed by the cross product of red to green and it could just be red to P as well. It doesn't matter which one you pick. And so we compute these 3 quantities, we add them up, capital R plus capital G plus capital B. That's that number right there, 120. And then we take the, we compute the fraction. This is the total, right? So R divided by the total is 100/120ths, which is 5/6. So when we're trying to figure out the color of this point, it's going to be 5/6 red, and it's going to be 1/12 because it's 10/120. So the fraction G is going to be, the fraction G over total is 10/120ths, which is 1/12. That's going to be the same for blue. And so the color here is going to be 5/6 red, 1/12 blue, 1/12 green. And then we're going to mix those together. We are doing 8-bit color, so expect rounding issues and things like that because we're dividing the color components into 3 parts, and so you're probably going to round down more than you should. And it'll represent being off by a point or so in the colors, which is not the biggest issue in the world right now. So we need to figure out if this math is correct. So what we're going to do is we're going to compute the area of this quadrilateral here, this quadrilateral here, which is green, and then this quadrilateral here, which is blue. So we're going to compute the area of those quadrilaterals, which is just the cross product. Okay. So let's see if we're doing it right. Okay. So snap that over there. Does that make sense to you guys? 1/12 of 255. Yeah. So the amount of blue that you would get. So the actual color output of this, the RGB value, which I'll do in rainbow color, the RGB value is going to be 5/6 times 255. 212. It's going to round down. It's going to be 212 red, and then it's going to be 255 divided by 12, 21, and 21. 21. So that is going to be the output color. Okay. So the closer we are to red, the bigger that quadrilateral over here gets. The further away we get from red, the smaller and smaller it gets, because the cross product computes the area of something. Cross products and dot products are really useful. Like if you want to compute the shadow of something, it's dot product. Hang on, my mom's calling me. All right. So, yeah, good. You got. Oh yeah, yeah. So turn on. Excellent. It's verified. So Bazykian, yeah, turn on both of those, and then you'll see on the palette over here, there's going to be like a water. There's like water lake, water ocean, water river. Drag them onto your landscape, and they should just appear. It wasn't working for me. I'm not sure why. The basic thing, the basic water volume thing, that was appearing, and the lakes would not appear in the preview, and then you'd run it, and they'd sort of flash. There's something weird going on. I need to figure it out, but give that a shot. Let me know if that works. Okay, so this is our theory. So we've got the cross product of this, and that's so blue to green crossed with blue to P or green to P. It doesn't matter. They're two different legs of the same quadrilateral. Is the size of the red one. Okay. Okay. So let's see if we can figure this out. And also, we should test to make sure cross product is actually working correctly. So let's just verify that first. So let's see out. So let's make a line segment. Named Bob, who goes from vector 0 to vector 1. So this is going to be a line straight down. So it's row 0, column 10 to row 10, column 10. So it's going down 10 rows. So it's a straight line straight down. So let's get a point. Point P. It's going to be at 0, 0. So we're going to cross product a line coming straight down with a line going straight left. And we should get something. So let's see if this works. See out, cross product equals Bob dot cross product with P. Let's just verify that our cross product is functioning as intended. If it's normalized, it might be creating problems if it's normalized, huh? Yeah, we'll have to think about this. Okay. Cross product is 100. Okay, so it's not normalized. Good. So we've got a line of length 10 coming down, line of length 10 coming across. So the cross product is 100 because the quadrilateral formed, right? So the calculation we did right there, right? We have Bob, which is a vector coming down. Bob, it's a vector coming down 10 units. And then we have P over here, which is 10 to the left. And so the cross product forms a quadrilateral with those two as the legs. So obviously the area is 100. So good, that worked. And then let's just verify that it works for 10 across, and we'll see like 3 down. So it's a line coming down by 3. This should return 0. 70. Okay, that's a problem. Let's see. No, did I do that wrong? I did that wrong, didn't I? I did that wrong. Right, sorry. 3 down, column 10. So it's coming down 3 units, and the cross product is 0. Okay. So for this example, P was here, and so the cross product of Bob with P is 0 because it creates a quadrilateral of no size. Do you guys get what's going on here? So we're verifying the cross product is working. You're a little confused? Not really? Okay. So
you can explain specifically why I mean, obviously you've shown that the cross product represents the area, but why it's important that we're finding area.
So if you have a vector from A to B and a vector from A to P, the cross product actually returns the area of this quadrilateral. That's actually what the cross product returns. Product. Do you guys understand that conceptually? Like, the cross product is the area formed by these two lines here. Like, do you guys understand that part? Okay. And the equation is was it sine of theta times the length of AB times the length of A to P. So if this is length 5 and this is length 5, if it's a right angle there, it's going to have an area of 25, right? Because it forms a square. And if sine is 0, it's going to have an area of 0. If it's in between, it'll have an amount of area proportional to the sine of theta. Are you guys with me on that? Like the length of A to B, the length of A to P, and the sine. This is the cross product equation for scalar cross product. The 3D cross product creates a vector of that magnitude at an orthogonal direction. Okay, which we're not worrying about. So to figure out how close we are to red, we have to compute the. Are you doing this again? You're doing this again? One note. You're doing this. Okay. We have to compute this quadrilateral here. What is that area? That area can be computed by the cross product of this line here, this diagonal. So that diagonal there, cross producted either with this line or with this line. It doesn't matter which. So the area of this quadrilateral here is the cross product of the line from blue to green and the line from blue to P, or the line from green to P. Doesn't matter which. Okay. And we should absolute value it, probably. Do we absolute value it? Can we get a negative number out of this? Let's check. So if we're going from 0 to 10, 0 down. 0
Well,
down.
if you just cross it backwards, you get a negative.
Right. I'm just going to verify this. Yeah, you can get a negative number. That might be our problem. We might be getting. So what
Oh.
right. We're not.
Yes.
We're not doing absolute value.
Take
here.
the absolute value.
Yeah, that's important. Okay.
I think I did that as well.
All right. No, we can't do that because we first have to check to see if we're within the triangle, and if we're within the triangle, all of them are going to be positive. So
That shouldn't matter.
we don't. So we actually don't need to do that. Yeah, I think I vaguely remember that yesterday from my sleep deprived state. So yeah, we can't actually get a negative in here because if any of the numbers are negative, we just don't do anything. It's not within the triangle. So so what we're going to do is we're going to figure out the area of this quadrilateral here. We're going to figure out the area of this quadrilateral here. We're going to figure out the area of this quadrilateral here. You guys see that? And we're gonna add the areas together and then figure out what relative ratio is red, which is green, which is blue. The closer we are to red, the bigger the red quadrilateral is. The further we are from red, the smaller the quadrilateral is. Yeah, that's why I wanted to sketch it for you. Yeah. Okay. All right. So, and we're going to go past our normal ending time here because I was looking at the landscaping and stuff like that earlier. All right. So let's come over here and let's verify this works. So first cross producted with P. So That's going to be A to B, and it's going to be cross-producted with P. Okay, and the cross product is using the first point, I believe, right? So the starting point is there, the ending point is there. Yeah, so it's cross-producted with the starting point of the line segment. Okay, so this is going to be, so if, let's see. Suppose first dot start is all red, second dot start is all blue, third dot start is all green. Like this, right? First, second, third. Then this is going to be red to blue crossed with red to P. So this is percentage of green. Do you guys see that? So the first line segment is this one. This is the first line segment here. I should use a different color. Rainbow color. Sure. So that would be the first line segment here. So this crossed with this. Oh shoot! Did I do the colors wrong? I did, didn't I? I don't even have a lack of sleep to blame this time. Okay. Sorry. Green's over here, so the opposite one over here is green. Sorry. Okay. And then the one opposite of blue is the blue region over here. Sorry about that. Okay. So we're cross-producting red to blue with red to P, and that's going to be our green percentage. Then the second line is blue to green crossed with blue to P, and that's going to be our red percentage. And then the third one is green to red crossed with green to P, so that's going to be our blue percentage, or relative, whatever, relative amount of blue. Okay, so now that we got that figured out, we compute the sum of all the cross products. That's the total. That's the total area of the triangle, basically, twice. All these things are twice the actual number, but it doesn't matter because we're doing division. Right, so if instead of adding 10 and 10 and 10, we add 20 and 20 and 20, we're still going to get a third for each one. So we don't need to waste divisions on this. So yeah, we've actually computed twice the area of the triangle at this point, but we don't need to divide by 2 because who cares? Okay, so yeah, and then we figure out which percentage. So this cross one is the percentage of green, percentage of blue, percentage of red, and now we just need to see if these numbers here actually make sense. Okay, so I think this is backwards. So cross one. Okay, so the first line is actually computing for the third point, so that should be 3, and let's see here, and the second one should, let's see. Your thing crashed. Huge. It's brutal. Okay, so for the first point, start is our red. So this guy, the amount of red, and the relative proportion is going to be the second one we did. So that should be cross 2. Okay. Then for our second point, which we're calling our blue point, that's going to be 1, 2. That's the third one. and then for the third one, that would be the first one we did. Okay, so it should be 2, 3, and 1. First ones are red ones. The second one should be the relative percentage. First one we did is Amelia, you see anything wrong with this? We might have to dive into adding things. Oh yeah, you did it too, huh? Yeah.
Yeah.
Yeah. Okay. We can do that if you want.
I'm working on my own cross product right now.
First, second, third, blue, red, green, blue.
I appreciate your use of the word Z. I mean,
yeah. Okay, we don't need that right now. Let's put this back up at 255.
That looks interesting.
Okay, the first point is at row 0, column 10, and it's red. The second one is at 1010 and is blue. Oh, maybe the line rendering's backwards. Look at that.
Yeah.
1010 is supposed to be blue, and it's green.
Is the line rendering doing its own rasterization?
It is. It's got a separate rasterizer.
Oh, that's probably where we should be looking.
Well, it's overriding. It does the lines after it does the inner part. But in fact, maybe we don't need to do that. Maybe we can just turn off the line rasterizer. Because that's what I did. For the line rasterizer, I was swapping the points if they're out of order, and so that might be what's going on there.
I mean, that's what I did. Oh yeah, you swapping the points is probably causing that.
No, look at that. Or am I?
Where else is this line?
Oh no, they're being rasterized up here too. Okay. It's not drawing the bottom row, huh? I mean that's correct.
Pretty much what mine ended up looking like.
That's actually correct, right?
Yeah.
Yeah, it's probably in the line rasterizer because I was swapping the things to make it.
You have to also swap the colors.
I thought I don't know, dude. I had like so little sleep. I just had. See, I thought I was just swapping the starting columns and rows, but I don't know. Yeah. So, somewhere in there, the colors got reversed.
Well,
so,
yeah.
Swapping the starting row. Yeah, it should just be switching the column in a row. It shouldn't be switching the colors. But for some reason... Oh. Yeah. Okay. Right. Yeah, that makes sense. Okay. Rather than doing this, let's just bite the bullet and do it for realsies. So if that... Okay, so we're going to go bool left to right, or I'll just make this int left to right equals 1, and if we're going to go right to left, then we're just going to set it to left to right. We're going to set it equal to -1, so we'll go this way. And then rather than I++, we're going to do I plus equals left to right. And then it will either go left to right or right to left. And that should hopefully fix it. Let me do the same down here. That's what happens when you find a hack and you want to stick with it. We'll call this one top to bottom equals 1, and if the starting row is bigger than the ending row, then we have to go bottom to top. Top to bottom. Minus 1. I plus equals top to bottom, and then let's do the line rasterization again. D3D. Paste. 2x dot dot 3 equals 3. That's still inside of the for loop. So once we finish the for loop, we'll do line rasterization. Crashed. Oh, yeah. Right. So, because we're going one way. If we go the other way, we never end, right? So annoying. Abs. So what we really have is we have 4 different ways of drawing a line, right? Left to right, top to bottom, right to left, and bottom up. And I'm trying not to duplicate as much code as possible. So that's our starting point. That's our ending point. Then if we have to go the other way, then we'll just call this step. Then we go, then the starting point is the ending point. I is equal to absolute value of horizontal distance. Trying to think of the way I could write this with the minimal amount of steps possible. You know what? I am just not going to worry about it. Yeah, so it's works fine when it goes in one of the directions. But what's happening here is that instead of going right to left, it's going left to right. And you can see it's actually doing the colors properly. And so if we're going to be doing right to left, then everything just needs to be offset, I guess. Again, I'm trying to figure out how to do this in as few lines of code as possible. All right, let's try this. There. Yeah, I'll just need to come in and clean this up when we're offline. I know what I have to do. It's just I keep, yeah, I know. Hey girl, we just need to. I'm just keep trying to think of a good way of doing this cleanly. Anyhow, so let's stop there. What I want you guys to do is to, and if we just don't do the line rasterization at all, here, let me make a note of that. Draw points to start and end. To do, it is currently buggy when drawing right to left or bottom to top. Okay. So right now we need to handle those cases. I'm just going to leave that as a note. We don't need to use it, so that's the good news. The good news is we actually don't need to draw the lines because we're doing triangle rasterization, not line rasterization. So, yeah, I know they're not used. Thank you. So there we go. They're actually coming out okay, and the colors are blending nicely. And I guess we don't really need the pluses either, do we? So, stop at a space, and. Okay, so there's a triangle. So what I'd like for you guys to do is make an animation. I'd like for you to make the triangle spinning in 3D space. You can watch the lecture from IS-50A today to see how you can do a 3D transformation matrix if you don't remember how to do that. And I just like, just record a little video of the triangles spinning around and they'll intersect each other. Maybe you can have don't have all of them be rainbow colored like this. So you can see the different triangles. And the lecture from today, yeah. We talked about how to do transformation matrices and things like that. So, yeah. So that is going to be your assignment. Vim, rim, out. Vim, let's do this. Figlet, animation, into readme. So, given assignment, given code to that does 3D rasterization and Z buffering of triangles operating over a vertex spool, make an animation that animates at least 3 triangles over overlapping each other. You mostly aren't going to have to write any of the rendering code, I think. The triangle should be fine. It should overlap each other fine. So all you have to do is do the rotations and things like that. There's 3 triangles overlapping each other. Have it so that sometimes one is in front and sometimes the other. Have the triangles okay, that's it. So shouldn't be too bad. What you're going to do is you're going to come in here in main.cc, make some new triangles. If you have them share coordinates, then they're going to have the same colors. So just make 3 different triangles, and then rotate the points in them. You'll probably want to write maybe a rotation class or something like that. Maybe have you make a transformation matrix. Seems like a good idea. And maybe write a rotation member function that updates the matrix. Then you rasterize all of the row call z data will go through that transformation to get a final row and column. Something like that. Okay. Maybe make a center point. Okay, so a little bit of linear algebra for you guys. Yeah, like what we talked about today in ISFDA, the general equation for rotation is you create a 4x4 matrix like this. These 3 numbers here are translation. The scale is by multiplying these 3 values by a number, and then that right there is your rotation. So it'll rotate around the origin. The origin's the top left part of the screen, so you might end up rotating it off. So you might want to create a center point. So if the center point is like over here, then you translate the triangle over the origin, essentially rotate it, and you translate it back. And then the triangle will rotate in place rather than rotating around the origin. So, but if you want to start with just this, and you do a rotation around the origin, you'll see the thing just kind of swinging around the top left corner of the screen, and that's, I guess, fine too. So, yep. So this is for rotation around the z-axis. The z-axis going through the top left corner of the screen. If you rotate around it, it'll just kind of swing around like this. It'll look like this. So if that's the top left corner of the screen, so you're not going to see it rotate in place, you're going to see it swing right off the edge of the screen. So if you want to rotate it in place, you translate it over the center point, rotate it, and then translate it back. Okay. So I think this will be a good final C++ programming assignment for you guys. Ultimately, I just want to see a couple triangles just rotating in place on top of each other, different colors, so you can see sometimes one triangle comes in front and then sometimes the other triangle's in front. Just have 3 of those spinning, and that's good. Maybe I'll make it the splash screen so that when people log in on the server in the fall, the students will be greeted by your triangle demo, you know, doing one of these things, and they'll say welcome to the matrix or something like that. Access granted, you know. Blow their minds because it's a text-based interface. It's like that'd be cool, actually. If the triangle zooms in, you know, rotates. I don't know. Cow save will be replaced. Yeah, yeah, that'd be cool. That'd be really neat. And I mean that literally. Like, if you guys do something cool, I will actually use it as like the login thing. You know, three triangles rotate, you know, and they fly together or something. I don't know. Yeah, okay. There's code to rotate. All right, cool, nice. Enter the angle for rotation. X1, Y1, X2, Y2. So that's going to rotate all 3 points in a triangle. Okay, yeah, sure. There you go. There is operational rotation code. So that's the full thing. What I showed you was just for rotating about the z-axis. But just remember that if you're going to be if you're going to be rotating around an axis, because these are rotating angle for the rotation, that in general they rotate around the x, y, and z axes. And so before you do that, set a center point on the triangle. I know I got to go, but let me just show you what I mean. So if you were to rotate this triangle here, if you were to rotate it 90 degrees, it spins around the origin here, right? And so we usually don't want that. We usually want it to like rotate in place. And so what you need to do is set a center point. So if you have a center point on a triangle, like let's say this point is 5, 5, and you rotate it 90 degrees, what you want, or well, that wouldn't be very interesting. So you rotate it like a little bit, you would get this, right? Or that's still 5, 5. You want it to spin in place. And the way you make that work in the code is what you do is you translate this guy 5 left, 5 down, put it here around the origin. Here's the origin of the world. Then you do the rotation, and then you translate it back. Okay, that's easy peasy. There's faster ways of doing that, but that's pretty simple. So you take all the points, this point here, this point here, this point here. Each one of them is going to get rotated. 5 left, 5 down, rotate, and then 5, you know, and then put it back. 5 up, 5 right, you know, and then you'll see this triangle just spin in place. But you need to give it a center point. Okay. You need to find the center of a triangle. You can do that automatically if you want, or you just set it. And it's up to you. It's just the Barycentric is actually one way of doing it. But it's just yeah, you make a bounding box or something. I don't know. Or let's see. You can project. Yeah. Okay. I gotta go. All right. So that's your homework, and Ada, say goodbye to my students.
Goodbye.
And I'm gonna go hang out with my daughter. All right. See you guys. So there's rotation code for those of you at home, if you want to do it that way. All right. See you.